Hey folks, today what we're going to do is we're going to talk about drawing some Lewis dot structures. So this is notes 3.2 on covalent bonds, talking about Lewis dot structures. So Lewis dot structures are, let me show you what I'm talking about here, these guys. So it's a combination of your element and then a bunch of dots around the element. Now remember from last lesson, the dots around the element symbolize the number of electrons. So for example, here, fluorine has 7 valence electrons. Valence electrons, not just regular electrons. Fluorine has 9 regular electrons, 7 valence electrons. So we put 7 dots around there, 1 for each valence electron. So in order to draw a Lewis dot structure, that's the first thing you do, is you draw the letter of the element, or letters, and then you draw all the dots for each valence electron. So in this case, we're looking with the structure F2. That's 2 fluorines. So I drew 2 fluorines, each with 7 valence electrons. And then what I'm going to do is I need to form a covalent bond. Now, remember, a covalent bond is all about sharing. So I'm going to want to kind of connect the dots here. That's the next step. Or form a bond. So by drawing a line between this F and this F, I can form a bond so each atom has 8 valence electrons. So what kind of happens in terms of the element view, you might remember this from yesterday, is that, remember, the elements go super tight to each other, and kind of in that blue circle, that's where they're sharing the electrons. But then remember, we don't show electrons being shared as 2 dots. Instead, what we show them as a single bond, or a line, kind of connecting those 2 fluorines. So what you'll notice here is that this line shows that the fluorine on the left has 2 electrons shared in this bond, and the fluorine on the right has 2 electrons shared in the bond. Then, kind of counting them up, we have 1, 2, 3, 4, 5, 6, 7, 8. Remember from yesterday, 8 valence electrons is stable. It's what just about every element wants to get to, except for hydrogen. We'll talk about that. So yeah, both fluorines here have 8 valence electrons. The total number of electrons haven't changed. Remember, each had 7. So there's 6 on the outside of each fluorine, and then 1 in the middle there. So there's still a total of 7 electrons for each fluorine, or a total of 14 for the whole thing. And everything has 8. So everything's got 8. Everything started and ended with the same number of valence electrons. This right here is a correct Lewis dot structure. We're going to do a couple more difficult examples of Lewis dot structures as we move forward, and we'll show you a more complete set of rules. But for now, kind of the 2 rules are, make sure everything has 8 valence electrons, and make sure the total number of valence electrons are present. So maybe make sure that you don't lose any total valence electrons. So for example, you have 14 here, make sure you don't end up with 12, or make sure you don't add extra, so make sure you don't end up with 16 instead of 14. So yeah, make sure you start with the same, and everything has 8. Those are the 2 rules. Great, moving on here. Okay, I said every nonmetal wants 8 valence electrons. That's true for everything except for hydrogen. Let's talk about hydrogen. So first off, we got to talk about noble gases though, because this is where things are actually stable. So helium, neon, argon, krypton, xenon, and radon, all these things in purple here are our stable noble gases. Remember, helium has 2 valence electrons because it's kind of an exception, and all the other noble gases have 8 valence electrons. In general, we'll just say 8 valence electrons is stable. And that's true for everything in yellow over here. These are all nonmetals. Some of them are metalloids, but they're all nonmetals, and they all have either 4, 5, 6, or 7 valence electrons, kind of depending on which column they're in. Carbon and silicon both have 4. Oxygen, sulfur, selenium, and beryllium over here both have 6. And all the halogens have 7, for example. So what they want to do is they want to take their 4, 5, 6, or 7 valence electrons, and they just want to get to 8. So for example, carbon is going to have to share until it gets an extra 4 electrons, versus something like chlorine over here would just have to share until it gets 1 valence electron, 1 extra valence electron. Either way, both of them are going to have 8. That's true for every nonmetal. It's going to share until it gets 8, except for hydrogen, because hydrogen's over here with just 1 electron. And if you look at helium, its stable noble gas equivalent, the one that it wants to get to, helium's only got 2. So in the case of hydrogen, it's stable as soon as it has 2 valence electrons. So what that's going to look like then is hydrogen is just going to want to form 1 bond, and that's it. versus all these other things will want to form maybe one bond. For example, the halogens will form one bond and then have 6 dots around the outside. Everything with 6 valence electrons will need to form 2 bonds, and then they'll have 4 valence electrons around the outside. Everything with 5 valence electrons will form 3 bonds, and everything with 4 valence electrons will form 4 bonds. Just because in this case here with carbon and silicon, they need 4 extra electrons, so 4 bonds. With nitrogen, phosphorus, and arsenic, they need 3 extra electrons, so to get to 8, so then they're going to need 3 extra bonds, 2 extra bonds, and 1 extra bond, respectively. But hydrogen just needs 1 bond. So we're going to show you the compound HF, so kind of we're just replacing, instead of F2, now we have a hydrogen instead of a fluorine. Here's what fluorine looks like with its 7 dots, its 7 valence electrons. Here's what hydrogen looks like with its 1 dot, its 1 valence electron. In order to get both of these stable, first thing we have to do is connect the dots. And that's also kind of the last thing we do. Now, what you'll notice here, I kind of kept these circles up just so you can kind of count out and see that fluorine here has 8 valence electrons. It's sharing these 2 in the middle, one that it used to own and the other one that it's kind of sharing with hydrogen. So now it has 8. And hydrogen, it's got the one that it owns, and then it's got the other one that it's sharing to get to 2. So in this case, fluorine is stable with 8, and hydrogen is stable with 2. So when you're looking at hydrogen, don't put dots around it, just form 1 bond and you'll be good. It's kind of a little bit tricky, except as soon as you know that rule, then it becomes actually really, really easy because you don't have to keep track of any other electrons. Yeah, so that's the takeaway here. Every hydrogen needs 1 bond, which is just 1 line and no dots. So definitely write that down. Moving on. Okay, these are terms that I'm going to throw at you, shared electron pairs versus unshared electron pairs. Here's what you need to know. A shared electron pair is a bond or a line. So taking a look at this example of F2 down here, you'll see that we only have 1 example of a shared electron pair in this specific molecule of F2. For unshared electron pairs, that's any times you see that there's 2 dots. So in this case, we see a bunch of 2 dots. In fact, we see 6 of them. There they all are. Other things we'll ask you to do is we'll ask you to be able to count up the total number of electrons. Now, looking at this, you might think, well, I've got a total of 12 dots, so that must mean I have 12 electrons. But don't forget, this bond right here, this line, is actually 2 dots kind of hiding. So the total number of electrons here is actually, if you count them all up, 14. So dots and bonds is kind of what I think about when I think of total number of electrons. Another way of looking at this is kind of a smarter way. Instead of counting up each individual atom every single time, one of the ways to save a little bit of time is you can actually just count pairs. So a group of 2, that's a pair, 2, 4, 6, 8, 10, 12, 14. That's a little bit helpful. Or you can just think of it as, 7 pairs. So 7, either 2 dots or bonds. So it's kind of nice to think of things in pairs just because bonds always have 2 electrons and usually atoms will have electrons and 2 dots. We won't give you any atoms that are stable when they just have 1 dot by itself. That doesn't happen because you need to get to 8 and 8's an even number. So in order to make that happen, you need pairs of dots. Cool. Moving on here. Okay, this is kind of a, let me see here. Oh, we're going to talk now about drawing Lewis dot structures for individual atoms. So what I'm going to do is I'm going to show you hydrogen with 1 valence electron, helium with 2 valence electrons. Remember, helium's kind of weird. Helium's the only example of a nonmetal that has 2 valence electrons. Boron's the only example of a nonmetal that has 3 valence electrons. Carbon, nitrogen, oxygen, and fluorine, these are the guys you're going to see the most right here. Things that look like carbon that have 4 valence electrons, things that look like nitrogen or oxygen or fluorine. That's what you're going to see the most of. You won't really ever see helium because it's a noble gas that doesn't bond. You won't ever see neon because it's a noble gas that doesn't bond. You won't really even see boron just because it behaves weirdly and it's kind of an exception. But anyways, let me show you what Lewis dot structures would look like for these elements. So here's the element: hydrogen, helium, boron, carbon, nitrogen, oxygen, fluorine, neon. So kind of 1, 2, 3, 4, 5, 6, 7, and 8 valence electrons respectively. First thing we're going to do is we're just going to show you dots. Again, focus on hydrogen, carbon, nitrogen, oxygen, and fluorine here. Um, Kind of the point here with these 5 elements is that everywhere you see a lone electron, a bond will form, is kind of the idea. So in the case of oxygen, remember we said it has 6 valence electrons. So to get to 8, it needs to form 2 bonds. And those 2 bonds will form on those 2 lone electrons. With carbon, it's got 4. The only way for it to get to 8 is to form 4 bonds, right? It can't gain electrons from any other way. It can't take them away, and it can't give those 4 electrons that it has away. With nitrogen, it's got 5, so it's going to want to form 3 bonds. And fluorine has 7, so it's just going to want to form that 1 bond. So here's me kind of writing down the number of bonds each one has. And what I'm going to do now is I'm going to replace these single dots with actual bonds. So a hydrogen with 1 line is stable with 2 valence electrons. Ignore boron and helium. A carbon with 4 lines is stable with 4 bonds. It's got 2, 4, 6, 8 valence electrons, because remember, each bond is worth 2 valence electrons because they're being shared. Nitrogen is stable as well, 2, 4, 6, 8. It's got a pair here, and then it's got 3 shared pairs. So unshared pair and 3 shared pairs. Oxygen has 2 and 2, 2 shared pairs and 2 unshared pairs. Fluorine's got 3 unshared pairs. It's got 3 sets of 2 dots, and then it's got 1 line or 1 shared pair, 1 bond. This is true about 95% of the time. Every once in a while, we'll work with a weird thing that doesn't really work this way. Like every once in a while, carbon might only form 3 bonds, and it might take an electron from something. It doesn't happen more often than it does, so we'll go over those exceptions in quite a bit of detail. Okay, so here are the rules for drawing loose dot structures. Unfortunately, this is where the most writing comes into play. You're going to want to know these rules. We'll boil them down as we move forward, but sometimes when you're first starting these out, it's a little daunting. So here are some steps that you can always follow that'll kind of help you out. The first step is place the atom that can form the most bonds in the center. So you're going to have to think of this. In this case, we have CH4 that we're kind of drawing as we're writing down the rules. C is carbon and H is hydrogen. Hydrogen each has 1 electron, so it'll form 1 bond. And kind of the general idea here is that you can't put hydrogen in the center because it only forms 1 bond. You couldn't put hydrogen in the middle and you can't form 4 bonds out of it, but you could with carbon. Lewis dot structures will always have a center atom. Kind of how I think about it is you always put 1 atom in the center and then start by putting an atom to the left and the right of that. If you have more, so in this case, we've got a total of 5 atoms, 1 carbon and 4 hydrogens. So if you have more than just 3 total atoms, then you put 1 above the center atom and 1 below the center atom. And that's where you get like 4 and 5. So carbon's going in the middle because it can form 4 bonds versus hydrogen can only form 1. And then we're just going to put hydrogens around. Now you'll notice that I was pretty strategic in where I put hydrogen's 1 valence electron. I put it in a way that I can do the next step. And the next step is give each atom its number of valence electrons. And then we're going to connect everything together. So the rules so far are find your center atom and then connect the dots. I'm going to pause for a quick second.
I pledge allegiance to the flag of the United States.
Okay, so yeah, like I was saying, you give each atom its number of valence electrons, and then you're going to connect the atom with at least a single bond. Oh my goodness. Sorry about this. Yeah, so that's pretty much it. Once you have everything connected with a single bond, the only last step you want to do is you want to double check. Make sure each atom has the correct number of electrons it's supposed to have. So in this case, carbon needs to have 8 and hydrogen needs to have 2. So each 1 bond coming from hydrogen means they all have 2. So that's great. And carbon with 4 bonds coming off of it means it's got 2, 4, 6, 8. So 2 electrons from each bond, total of 8 electrons. Carbon's good, hydrogen's good. Remember, the 2 things you want to make sure of in every Lewis dot structure is octet rule, so each atom has the correct number of electrons, and then the total number of electrons. So you have 4 electrons from hydrogen and 4 electrons from carbon. Sorry, 1 electron from each hydrogen, so a total of 4 there, because you got 4 hydrogens, 1 times 4 gives you 4. and then carbon's got 4 electrons. So your total number of dots is 8, and that doesn't change. You didn't add any dots, you didn't remove any dots, so you're good. So total number of electrons, and then 8 valence electrons for each atom, which you satisfy here because hydrogen just needs 2. Okay, coming up, we've got 2 practice problems. I'm going to go ahead and go over them, and then we're going to end the video. So if you feel good about this, I would go ahead and try these out on your own. If not, follow along with me. So for this problem here, again, we've got to figure out which atom is kind of our center atom. So I know phosphorus, looking at my periodic table, has 5 electrons. Hydrogen has 1. And then I'm going to have 2 iodines here. And iodine each has 7. Okay, so making the choice here, I'm going to have 3 things on the outside and 1 thing in the center. In this case, phosphorus is going to go in the center just because it's got the most number of bonds that it can form. Think, it has 5, needs to get to 8, so it's going to end up forming 3 bonds. So I'm going to put a dot here, here, and here, and then a double dot up top, a pair. Let's put the hydrogen over to the left, just because I feel like it. And we're going to put our iodines 1 to the right and then 1 down below. Again, doesn't really matter where you put them. Okay, hydrogen's got 1 dot next to it, and each iodine has a total of 7 dots. So I'm just going to kind of dot everything up. There's 7, 2, 4, 6, and 7. And then here's 7 over here, 2, 4, 6, and then 7. Great. So I have all of my dots accounted for. Now the last thing I have to do is kind of just connect dots. You'll notice here I was strategic in where I put my lone dots. I put them close to each other so that it kind of looks nice when I connect everything up and it looks fairly organized. Okay, looking at phosphorus here, I've got 2 electrons from the lone pair, and then I've got 6 from each of my bonds. So 2, 4, 6, 8. Phosphorus is stable. That's awesome. Looking at this iodine over here, I've got 2 from this bond, and then 4, 6, 8. So iodine is stable. This iodine over here, 2, 4, 6, 8. So both these iodines are stable, and my phosphorus. And then my hydrogen is stable as well. So does everything have 8? Yes, it does. Is my total number of electrons the same as what I started with and what I ended with? Well, I've got 1, 2, 3, 4, 5. I've got 1 from my hydrogen, and then I've got 7 from each of my iodines. So in terms of total, yes, everything is also stable. Go ahead and try this next problem out as well. Awesome. We're going to go over it. Pause if you need more time. Carbon's got 4. Hydrogen each has 1. But remember, there's 2 of them, so I'm going to have 2 H's. So I have a total of 2 from both of my H's. And then bromine each has 7. Hopefully what you notice in this problem here is that hydrogens and things with 7 valence electrons, halogens, they always form 1 bond. So I can't put a bromine in the middle because I need to form, 5 or 4 bonds. And I can't put a hydrogen in the middle, again, because I can only form 1 bond for my hydrogen. So hydrogens go on the outside, and bromines are also going to go on the outside. So put 1 bromine on the outside, another bromine on the outside. The rule here is carbon kind of always is going to go in the middle. I can't think of right now a single example where it doesn't. And then just kind of dot everything else up. So here's bromine with its 7. Here's another bromine with its 7. And then we kind of, once again, are going to connect everything here. Connect everything. Connect everything. And you can kind of always do this right away. Bromine's got 8. Other bromines got 8. Hydrogen both have 2. And everything's got 8. So we're good on the 8 valence electrons. And since we drew all of our electrons to start, we know our total number of electrons did not change. We didn't add any, we didn't remove any. So those are the Lewis dot structures for those 2 problems. Here's it a little bit more nicely worked out for you. I don't know if that's hard to see, but I kind of tried to draw them out a little bit. Okay, anyways, that's where we're going to end it for today. So thank you so much for tuning in. Have a great rest of your day. We'll see you next time.